Welcome to the deep dive. Today, we're sort of strapping on our conceptual gear and taking a plunge, a really big plunge into Lake Michigan. But importantly, we're not paying professional prices to do it. Our mission for this deep dive is really to give you the blueprint, a guide for cost-effective deep water exploration in the Great Lakes. We want to show you exactly how you can build a functional underwater drone, something that can actually navigate that huge hidden world down there. This is technology that, honestly, it used to be just for big research labs, universities with huge budgets. We want to show you how to bring it home. And the cost comparison, well, that's really what anchors this whole thing. If you look at professional autonomous underwater vehicles, AUVs they call them.
Like the really sophisticated ones.
Exactly. The kind used by places like the University of Michigan. You're talking tens, maybe hundreds of thousands of dollars just for the basic unit.
Yeah, it's a different world, cost-wise. But what's really revolutionized this field is, well, the accessibility of the components now. Our sources are pretty clear. If you embrace that DIY mentality, you can build a really functional ROV, a remotely operated vehicle, for Lake Michigan for less than $1,000.
Less than $1,000, seriously.
Oh, yeah. And for basic builds, something to get you started, maybe $300 to $600.
That's a radical change. Because even the commercial consumer stuff, right? For similar features, depth holding, decent video.
Yeah, the off-the-shelf ones.
You're still looking at, what, $2,500? Maybe $4,000?
Easily. So the DIY route, you're getting a tool that's 60, maybe even 80% cheaper.
That's incredible.
It totally changes the game. It creates this massive entry point for the citizen scientist. This price drop, it just transforms how we can monitor the Great Lakes. We're moving from these really controlled, super expensive expeditions.
Right, the big ship science.
That's exactly. Towards more distributed, community-based monitoring. And research groups like the DRB mentioned at U of M, they're actually starting to use data from these advanced amateur builds. They see them as valuable, customizable tools.
Okay, so let's unpack that a bit. Why Lake Michigan specifically? What's this Great Lakes advantage that makes DIY builds so feasible there?
Well, the biggest advantage is pretty simple. It's fresh water.
Ah, okay. Makes sense.
Salt water is just incredibly corrosive. Electronics, motors, metals, it eats through them. In Lake Michigan, the fresh water is, well, much kinder. This means your waterproofing doesn't have to be quite as extreme initially. Your parts last longer. You don't need those super expensive, specialized marine-grade materials right off the bat.
So it simplifies the engineering challenge quite a bit. And the potential targets for exploration, they sound amazing. We're talking real historical exploration.
Absolutely. Lake Michigan is basically this giant, cold, dark, freshwater museum.
Huh. I like that.
We know of over 1,500 documented shipwrecks down there. Some go way back to the mid-1800s. And the water itself, it's cold. And it lacks those marine boring organisms you find in the ocean that destroy wood.
So the preservation is incredible.
It preserves these wooden and steel wrecks almost perfectly.
Right.
And your drone gives you a way to see them without disturbing anything. But it's not just shipwrecks. Geologically, you've got submerged caves, old shorelines from when the lake levels were different, huge fields of glacial boulders.
Wow.
And ecologically, you can monitor native fish. You can track invasive species like those quagga mussels, which are causing huge ecosystem changes right now.
Right. I've read about those.
And you can document fragile habitats. We've actually seen amateur explorers make real contributions, like finding unmapped colonies of freshwater sponges or rare bugs.
And this is where the modular design of a home build really comes in handy, isn't it?
Totally.
Like if you're near Milwaukee, you might focus your build on shipwreck photography, photogrammetry.
Right.
But if you're up near Door County, maybe you're more interested in mapping those underwater limestone cliffs. You can tailor it.
Exactly. You build the tool for your specific mission.
Okay, let's get into the nitty-gritty then. This is where people really need the details. The hardware needed to handle the cold, the depth, the sometimes murky visibility of Lake Michigan. This is where it gets interesting.
Right. First stop has to be the pressure vessel, the housing. For your first dives, say down to about 100 feet, and a lot of good nearshore wrecks are in that range, budget materials can actually work.
Like what?
Well, our sources suggest things like modified plastic electrical boxes, or more commonly, sections of 4-inch diameter, Schedule 40 PVC pipe, sealed up tight with marine-grade silicone or epoxy.
Okay, hold on. PVC pipe. Lake Michigan goes down over 900 feet. How safe is PVC even at that 100-foot mark? Are we trading safety for cost here?
That's a really important point. And yes, the PVC housing is suitable for that initial 100-foot zone where the pressure isn't astronomical yet. But you're absolutely right. If you want to go deeper, forget the PVC. you must switch to more robust designs, usually cylindrical, often using thick acrylic tubes with proper O-ring seals. Those are engineered specifically for handling that exponential pressure increase.
Got it. So PVC for starters, but upgrade for depth.
Definitely. And regardless of the housing material, there's one component you absolutely cannot skimp on: the cable glands, where the wires exit the housing.
Explain those.
Think of a cable gland like a specialized grommet, but designed to seal against pressure. It lets the tether wires pass through, but keeps everything watertight, even under pressure. Using cheap ones or skipping them, that's just asking for a flood, catastrophic failure.
Okay, critical component noted. Housing sealed. Now, propulsion. How do we get this thing moving and keep it stable in those lake currents, which can be pretty unpredictable?
For motors, you want brushless DC motors, and you need to seal them, usually in marine epoxy. For specific models, the T100 or T200 thrusters are kind of the gold standard for DIY ROVs.
Why those?
They just offer a great balance of power, durability, and size for the cost. Really reliable. And for stability against currents, you really need at least 4 thrusters. 2 horizontal for forward, back, turning, and 2 dedicated vertical thrusters. That gives you precise depth control.
Makes sense. What about the propellers themselves?
Yeah, you don't want props designed for high speed.
Okay.
In water, especially dense, cold, fresh water, you want torque. So look for wider, shorter blades. They give you more push at lower RPMs, better for maneuvering. Oh, and use shrouds, like a little duct around the propeller. You can 3D print it pretty easily from PETG plastic. They boost efficiency and, crucially, protect the prop from getting tangled in weeds or debris.
Good tip. Okay, visibility. This can be a huge issue, right? Lake Michigan often has that blue-green tint and light just vanishes at depth. How do we actually see anything?
Right, camera first. You need a wide field of view, 120 degrees, maybe more. And critically, manual white balance control. You need to be able to tell the camera, hey, ignore that blue-green tint. This is what white should look like.
Okay. Any camera recommendations?
A GoPro Hero, one of the more recent ones, if it's properly housed for the depth, is a great option. Good 4K video quality. But the camera alone isn't enough. You need serious lighting. Water just eats red light almost immediately. That's why everything looks blue or gray below, say, 30 feet.
So bright lights.
Very bright. LEDs, at least 1,000 lumens total, maybe more. And again, a wide beam angle, 120 degrees or so, to match the camera's view. But here's the key engineering trick. You have to minimize backscatter.
Backscatter. That's the annoying snow effect you see in underwater video.
Exactly. That snow is just the light from your lamps bouncing off millions of tiny particles in the water right back into the camera lens. To reduce it, you have to physically move the lights away from the camera lens. Mount them on arms off to the sides.
Ah, like car headlights in fog.
Precisely. If the lights are right next to your eyes, the fog reflects it straight back. Push the lights out, maybe point them slightly inward towards your subject, and you illuminate the target without blinding the camera.
That's a fantastic practical tip. Okay, last piece. Control. How do we actually drive this thing? Tethered. Autonomous. Especially on a budget.
For a DIY builder focused on reliability and getting started, tethered, definitely. You get instant video feedback and constant power down the wire.
What kind of tether?
The standard, cost-effective way is using a CT5e Ethernet cable, like for computer networks, but run inside flexible polyethylene tubing for protection and buoyancy. But remember, signal degradation is a thing. You're probably limited to about 100 meters, maybe 300 feet with that kind of setup before the signal gets iffy.
Okay. What about more advanced control?
Yeah, if you want to step it up, you can add semi-autonomous features. Using cheap controllers like a Raspberry Pi or an Arduino and open source software like ArduSub, well, then your drone can do things like automatically hold its depth or even perform a basic return to home if the signal drops.
Very cool. Okay, let's pivot slightly. We know the cold water helps preserve things, but it must be a nightmare for batteries, right?
Oh, it's the critical engineering challenge. Lake Michigan water, it rarely gets above 70 Fahrenheit, even at the surface in summer. And deep down, it's near freezing all year round.
And that affects batteries how?
Badly. Cold temps can slash the capacity of standard lithium polymer batteries by like 40 or even 50%.
Wow, half the capacity.
Yeah. You could launch thinking you have an hour of runtime and find yourself dead in the water after 30 minutes because the cold just sapped the battery.
Okay, so what are the solutions? How do you manage that thermal problem?
Well, thermal management is key. The simplest approach is passive insulation. Wrapping the battery compartment in neoprene like wetsuit material.
Does that work well enough for deep dives?
It helps, but for really deep water or winter exploration, you probably need active heating. Small chemical heat packs, like the kind skiers use. You can secure those right next to the batteries inside the housing. They provide a gentle warmth for maybe 6-8 hours. And for really extreme cold, you might even need to switch battery chemistry entirely. LiFePO4 batteries, lithium iron phosphate, they handle cold much better.
What's the catch?
The trade-off is energy density. LiFePO4s are great in the cold, but they just don't store as much energy overall as LiPos. So your max runtime might be shorter, even though they perform reliably in the cold. It's a design choice.
Cold performance versus maximum endurance. Got it. Safety and recovery have to be huge concerns too, especially with depth and maybe exploring historic sites.
Absolutely paramount. First, depth safety needs to be built in. Use good depth sensors resolution of 1 foot or better, and program fail-safes into your control software. Automatic depth limits so you don't accidentally crush that PVC housing if you're still using one.
And what if you lose it? It's a big lake.
Recovery is tough. You absolutely need a surface buoy attached to your drone, ideally with a GPS tracker on it. For emergencies, like if the main tether snaps, you can get acoustic transponders, or pingers. They can auto-activate if the connection is lost and send out sound pulses that you can detect with hydrophones, underwater microphones, up to maybe 1 kilometer away. Helps you find it again.
Okay. And you mentioned something about navigation near shipwrecks being tricky.
Yeah, it's a known issue. Big steel shipwrecks create magnetic anomalies. They can seriously mess with a standard magnetic compass, throwing your navigation way off.
So relying just on a compass near a wreck is risky.
Very risky. If you're targeting wrecks specifically, you really need redundant systems. Things like inertial measurement units or maybe acoustic positioning systems, not just the compass.
But on the plus side for the cold, winter exploration sounds like a unique opportunity.
It really is. Kind of the Great Lakes explorer's secret weapon. Well, yes, you have to cut a hole, maybe 24 inches wide, through the ice to deploy. But the payoff is visibility. With less biological activity in the winter, no summer algae blooms, the water clarity can be incredible, often over 50 feet. So shipwrecks that are kind of murky and obscured in July, they can look crystal clear in January. You just have to remember the battery thing and pre-warm all your electronics before you dunk them in that near freezing water.
Okay, so we've covered the bill, the challenges, the environment. What does all this mean for science? How can someone with a, $600 homemade drone actually contribute meaningful data?
It fills a huge data gap. Lake Michigan is just vast. Professional researchers can't be everywhere all the time. These amateur drones, they provide localized, continuous, high-resolution data that really complements the big academic studies.
How specifically? What kind of data?
Well, you can easily add basic, affordable sensors for water quality, temperature, water clarity using something like a SETI sensor analog, dissolved oxygen. If you log this data and, crucially, geotag it with GPS coordinates from the surface buoy, you're giving researchers vital information about conditions at specific places and times, stuff they often can't afford to collect otherwise.
And the shipwrecks, the archaeology side?
That's where that good camera and lighting really pay off. You can do photogrammetry.
Which is?
It's basically taking hundreds, maybe thousands, of carefully overlapped photos of the wreck from different angles. Software can then stitch these together into incredibly detailed, millimeter-accurate 3D models.
That sounds amazing. What's the use?
Those models are invaluable for preservation. Scientists can study the wreck, monitor how it's changing or degrading over time, all without ever touching the actual site. It's non-invasive documentation. And for ecology, think about invasive species. Using macro camera settings, you can get detailed images documenting the density, the spread, the patterns of things like quagga mussels on different surfaces or at different depths. That's critical intel for managing the ecosystem.
So this isn't just about taking cool videos, it's potentially structured data collection.
Exactly. That's the goal, to make the data useful. Operators can submit their georeferenced images, their sensor logs, to official portals, like the ones run by the Michigan DNR or similar agencies. And universities are getting involved too. Places like the University of Wisconsin's Water Science Program, Michigan Tech's Great Lakes Research Center. They're actively looking for ways to partner with these citizen science networks, sharing data, maybe even collaborating on new sensor designs for DIY drones. It's becoming real collaborative science.
This has been a fantastic deep dive. So the key takeaways seem to be: building a capable Lake Michigan Explorer is surprisingly affordable, way cheaper than commercial options.
Right.
You can do it with readily available parts like PVC brushless motors, but you need specific adaptations for the lake. Dealing with the cold's effect on batteries, using powerful, well-placed lights for visibility, and ensuring your thrusters can handle currents.
Yep, those are crucial.
And maybe most importantly, these DIY projects aren't just toys. They can contribute real, valuable, verifiable data that scientists actually need.
That's the exciting part, I think. The potential for contribution. Oh, and just a quick note on legality. Generally, recreational observation and photography are fine,
Right.
but you absolutely must be respectful of historical sites. Keep your distance. And if you're planning focused shipwreck exploration, especially in known preserve areas, always check first. Contact the Michigan DNR, the Wisconsin Historical Society, whoever manages that area. Ignorance isn't an excuse if you disturb something important.
Good advice. Always check the rules.
Definitely. And maybe here's a final thought for you to chew on as you start thinking about your own build. We talked about condensation, how it can form inside sealed electronics when you move the drone between the warm surface waters and the really cold, deep layers in Lake Michigan.
Right. That temperature difference is huge.
Exactly. So given that massive thermal gradient, what other maybe completely unanticipated mechanical or thermal things might your drone reveal? What weird phenomena might pop up when you plunge your specific build into those depths? It's a huge complex system down there, something to mull over while you're ordering that PVC pipe and those cable glands.